value, I should be able to or rather given an input message and the hash value, right? Preferably in the order of a few cycles of computational power. Right? It's typically a one-way function. While it is easy to compute the output from the input message and the initial hash value, the reverse should not be true, right? Given an output, I should not be able to compute the input or the hash values, right? I will not be able to compute the input because I have used a compression function over here, and this is a lossy compression function, which means I've lost construct, right? So it should be a 256-bit value, right? So the chances of two input messages creating the same hash output, it's ridiculously low, right? It should be as collision resistant as possible, and in case that there is a collision, there should be a provision for a collision resolution as well, right? Whether it is a rehashing mechanism or something else like that, it's perfectly fine, right? The final point is that or the penultimate point that I wanted to talk about was this avalanche.
Live streaming has stopped.
This avalanche.
Live streaming is on.
This avalanche effect, which is essentially, even if there is a 1-bit change in the input message or in the initial hash value, my there should be a multi-bit change in the output, so that I cannot run statistical packages in order to guess the input or the outputs, right? And that is where the puzzle friendliness really comes in, right? Knowing the hash of X and part of X, it should still be very, very difficult to find the rest of X, right? So that's the secure hash algorithm. And why do we use this hash algorithm?
Today we seem to be facing a lot of network issue. Please wait for a while. Let the speaker connect. Yeah, Akhilda, can you unmute yourself?
Can you hear me?
Yes, you're audible. Just share your screen.
But this time it is much more responsive. So typically, sorry for that, for the inconvenience, right? But where I was essentially saying that when you talk about this proof of work, right, you are essentially now creating a mathematical formula in order to secure a block of transactions, a set of transactions, right? And why does this work? I remember I told you that you need to know why can we provide security in this kind of a system, right? So let me try and simulate how this proof of work really it really works. Mm. I hope that is clear. So I have a small function over here, and what this function does is very simple, right? I have a string, right, and the string can be really anything. This is my transaction, right, which says Orun pays Mala 5,000, right? And what I want to do, I have used this is written in Python, and what I have over here, I'm using a hashlib function, essentially to be able to do the SHA function, right? So what I want to do is I want to run the hashing function such that I want my output, my proof of work to be essentially one. So I want to find out that if I were to create a hash function of this string with nouns that I'm starting from, zero plus, a random number, right? How many times do I need to go through before I find a proof of work match, right? A proof of work match is, in this case, I'm looking at a target string that is starting with 10, right? And what I'm going to do, I'm going to run this 5 times. Okay, very quick run, right? On an average, I saw that I found an entry. For example, this particular output, this is the SHA-256 output in hexadecimal for that particular string. And I started with a random number, with incrementing this number itself, right? 9, 10, 11. I was trying out with different numbers, right? You can easily see that changing one bit in the input led to a completely different output. This is essentially the avalanche effect that I had talked about. My target string has to start with 10. I got an output that starts with 10, and I found it in about 90 tries, right? Average time taken is about 0.15 seconds, and I ran it 5 times. And on an average, I took about 25 runs, right, for each of them. Now, let me just modify that and say that, okay, I want to find out what would be the time if my proof of work was 2, right, which means I'm going to try and find a number such that I start off with, that number starts off with 2 zeros. And again, like the previous example, I'm going to run this 5 times and see what is the average. Right. So last time we were averaging about 25, and this time around I'm now averaging 194. Right. I took about 0.15 second in the last run. This run I'm taking 0.87, right? So that's almost 6 times increase in the time required for execution, right? And I'm just starting off with 2 zeros, right? What happens if I try out with 3 zeros, right? I want to have a target string, a target output that starts with 3 zeros. Right. So my average time required went up from about 0.8 seconds to about 4.3 seconds, right? And the number of tries went out from about 190 odd to about 1500, right? This will start giving you a sense of how it becomes increasingly difficult, right? As I increase the proof of work, right? How much computation do I have to do in order to meet that proof of work requirement? So I'm going to try it out with a target of starting with 4 zeros, but I'm going to reduce the number of runs to just one because I expect the time to go up by an order of magnitude. And again, this time around, I'm just starting with 4 zeros instead of 3, right? I'm trying to find a magic number such that the output string that I create will start off with 4 zeros. And I'm going to let this run for a while because, you know, the entire security of a blockchain, right, is resting on just this algorithm. You have to understand that. The reason blockchain is hard to crack is because this computation is long. It is a really difficult computation to make, and I'm putting it up in front of all of you, right? Because this computation is long, this computation is hard, it is going to take up a lot of computation, right? It is going to take up, I am running this on an iCore 5 machine, which is a quad core machine, right? Even then it is taking up significant amount of time, right? It will give you a sense that if I have to reach a proof of work of 30, I cannot run it on laptops. I cannot run it on server grade machines. I have to run hundreds and hundreds and thousands of GPUs in order to do this kind of number crunching. And running all those computation costs me electricity, cost me resources, physical money. So the security comes in from the fact that trying to crack a blockchain based system is going to be computationally so hard that the costs involved in trying to crack it will be far more than the benefits that might be gotten out of it, right? Even in the last run, I think we got to about 1900 odd. We found a match over there. I'm just trying to find something that will close with the target string of with the proof of work difficulty of 4, and I'm finding it hard. So while this computation provides one of the core basis for providing security in blockchain systems, you also get a sense that blockchain or cryptocurrency is it's very energy intensive. It is very it is not a very favorable solution when it comes to carbon credits and its impact on the environment, right? What about the runs here? Priyaranjan, this is I'm just doing for a run of starting with 4 zeros, right? If I have to do, and you are seeing that for every zero that I'm adding, my execution time is going up by an order of magnitude. Last time round, it was in the tens of seconds. It's already gone up to about 3 minutes or 194 seconds, right? Last time we found a match in 1900 right, runs. This time round, we are looking at 48,000, almost 50,000 runs. If I were to add one more zero, it would take me about 30 minutes. If I add one more zero, it will take me about what 1900, that's about 30 minutes, 10 times of that, so that's almost close to 5 hours of computation on my computer. So with a proof of work of only six or seven, in order to get to a proof of work of 30, it's going to be computationally almost infeasible. And that is the brilliance of this paper, right? We are just asking what noun satisfies this hash of ledger plus nouns to the proof of work difficulty, and it's a very complex not a very complex calculation. You saw that computing each hash value did not take me a lot of time. The forward work was very simple, but finding this, iterating to find the nouns, that was the difficult part. And essentially, the security comes from the energy cost of this particular computation, right? That is why with cryptocurrency you have mining systems, right? You have mining systems which are rigged together with a large number of GPU machines that are strung together in order to find this particular nouns, right? Also, you have to understand that that the likelihood of a fraud only happens when the payoff that you get from that fraud is more than the cost incurred in creating that fraud, right? As long as you have made it asymmetrical, the chances of the fraud is going to be extremely rare, right? Or almost non-existent, right? So what's the fundamental innovation of blockchain over here, right? When we get a bunch of these transactions, right, we group them together, identify a noun so that we can create this block, and we keep the previous hash in the next block itself. So this chain of blocks is essentially what blockchain is all about, right? If I have to if there is any change in any of this transaction here, this previous hash will not match the hash of this block. These two values would kind of fall out of sync, and that lets us know if we can trust if there has been any change made to a transaction after it was inserted, right? That's the way security is guaranteed. And once we know for sure that a block is secure, we do not really need to know the whole genesis of it, right? We can assume that that is where the ground truth starts from, right? So currently, the way it works with blockchain, with Bitcoin, is that the proof of work is defined such that it takes about the proof of work kind of adjusted every 2 weeks or so, and it's adjusted so that a new nouns can be created by one of the mining machines about every 16 minutes or so. But who will get that is a matter of it's a flip of the coin, right? So the way this protocol now works is all new transactions are kind of broadcast to all nodes, right? When it is broadcast to each node will kind of collect the transactions in the order that they are seeing it in, and it will try to compute a noun such that it can claim this block as the main ordering, right? Once any node identifies a particular nouns and creates a block, it publishes that block to the entire group, right? So any node which was working and trying to find an ounce of its own. Once it receives one of the new blocks, it kind of discards work on its existing block, and accepts this new block with a certain degree of confidence, right? Now, it is very much possible that while the set of transactions that were being broadcast was being, everybody was being truthful, one node decided to play adversarial and decided to insert a new transaction or a fraudulent transaction, right? Therefore, the fact that I've received a new block does not guarantee that the block is valid, right? So in that case, what happens is I keep there is something called the longest chain rule, where I accept a new black block transiently, right? I accept it, but I wait for the newer blocks to arrive, and if there is a conflict, I take into account the longest chain that is forming, right? So each of these blocks, new blocks that are arriving, will have a hash of the previous block, right? The moment I don't have a hash of the previous block, I know that there is an inconsistency, right? Why do we have this longest block rule? Because an adversary can have control over a small percentage of the computing resources of the entire group, right? The probability of a new block coming from a group of adversaries is proportional to the computational resources they hold in that particular group, right? The only way where the adversary group can continue to create, or there is a higher probability of a new block coming out from only the adversarial group, is when they have that the adversary controls more than 50% of the computational resources of the network. Now, democratically speaking, if anybody controls more than 50% of the computational resources, their version of the truth is democratically the truth. So that's how you ensure that whatever the majority believes in, that is propagated in the transactions that are getting recorded, right? So trust grows with age because majority of the network will produce blocks faster, right? And this is how you essentially create a blockchain network, right? You essentially build about a consensus without a centralized trust in the network, right? And it essentially achieves a solution to the Byzantine general's problem by essentially creating a consensus mechanism with more combined difficulty. It is not difficult at an individual level, but at a combined level, it becomes extremely difficult to create falsified messages, right? It will get caught in the system, right? So again, if I break down the blockchain systems, right, what we find is that there are there is a mempool, right? The mempool is essentially where there is a pool of yet unconfirmed transactions. So all new transactions come into the mempool, and then you have mining computers or miners or mining pool, which is doing this proof of work to create the new blocks, right? The miners are computational nodes, right? So each of them are competing for creating the new block, because there is a reward for the miners in order to do so. They may get a part of the Bitcoin for performing this work. And these blocks are published to the full nodes and the pruning nodes, right? The full nodes maintain the full nodes maintain the all the lists, and then but you do not necessarily need to go through all the previous transactions once you know that the genesis or the history is kind of verified. So you have some lightweight nodes which keeps maybe the top 100, the top 50, the more recently used blocks in memory, and they can always go back to the full nodes if they need to access the entire blockchain, right? The pruning nodes are essentially responsible for ensuring that not all nodes need to be staying, right? Whenever you have a set of nodes which have been validated, through aging and all of that, you can cut down on them and reduce your memory consumption, right? So lightweight nodes are the ones which are used by the wallets because you don't really need the whole information. You need the last few transactions in order to move forward with it, right? With a transaction. So those are the components, right, in the blockchain system. We are towards the end of today's session. So I will conclude with probably going through an overview or summarizing the cryptocurrency concepts that we kind of took in today, right? The first important concept was around digital signature, about being able to validate a message integrity through a digital signature, and being able to verify the authenticity of a signature and the message that was signed on through a public key infrastructure mechanism, right? So that gives us digital signatures, right? We saw how the ledger could be used as currency, as just passing somebody all my set of transactions will allow the recipient to know whether I am allowed to make a transaction or not. And by using the ledger as a currency, how we solve the problem of double spending, right? We saw how proof of work was created, how we are using computational workload and resource costs as essentially something that prevents something that can prevent an adversary from breaking into a cryptocurrency system or a blockchain system. We saw how the blocks are created and they are kind of chained together, right? They're kind of chained together so that you create this distributed set of records, right? Any portion of the blockchain can reside in any of the computers, or when you want to download all the transactions, you are allowed to do that as well, right? You can download the whole blockchain onto your computer as well, right? And finally, we saw how blockchain addresses the problem of distributed consensus, how multiple nodes agree on what was the right order of transactions that happened, right? While doing so, I want to emphasize that while we build distributed consensus and it can be mathematically proven that there is consensus being achieved at eventually in a blockchain-based system, right? Not every piece of code in a blockchain system needs to be distributed, right? So what you will find is, there is a difference between the usage and the underlying protocol itself, right? Whereas there is underlying protocol which talks about consensus, the mining and propagation of transactions to all the nodes, right? You can still build applications on top of it which are centralized applications, right? So the degree of decentralization that you want to build, right, or what is known as Web 3.0 today, right, it really depends on the architecture that you are trying to build, right? So in many cases we find these cryptocurrency wallets where the wallet itself, the mobile app for the wallet is being served from a centralized location, and your mobile phone is essentially connecting to a centralized backend which is serving you this page. Or with case of dApps, you can find that the entire code can also be distributed, but it's more complexity. The more components, the more distributed components you have in your architecture, the consensus protocol is going to get heavier and heavier, and will weigh down on performance, right? So it is purely an implementation architecture in terms of how much do you want to be decentralized and how much do you want to be decentralized. If you are completely decentralized, you pay the cost in terms of latency and the rate of transactions. If you have it too centralized, then it is as good as one of the existing IT systems, right? There's a single point of failure as well, even though the database might be distributed, right? So I'm going to probably stop in here today and start off with a SWOT analysis of blockchain based systems tomorrow. But in the meanwhile, whatever we have covered, if there are questions around that, I'll be happy to take those questions over the next few minutes. Are there any questions that I can take? We have 4 minutes on the clock. Are there any questions that I can take today? Today's talk was a little bit more philosophical. Today's talk was a little bit more about understanding, developing a deeper understanding of where the trust comes from in a cryptographic system. And over the course of the next few days, Reshmi and team will be taking you through leveraging this trust to build smart contracts, right? Ethereum systems where the transaction itself, right, what you are encoding as the transaction is not just a transaction between two parties. It is actually a piece of code that needs to get executed when a certain condition is met, right? Those are called smart contracts, and blockchain systems can be used to execute on those codes code dynamically in case of smart contract based systems, right? Uh, I think we don't have time to go into the SWOT analysis today. We'll cover that in tomorrow's session, right? And we will also start looking at the framework that has been proposed by the government of India with respect to how do you evaluate a particular use case and and the applicability of blockchain to that particular use case, right? What are the various case studies and implementations that are available from the NITI Aayog, right? Where blockchain-based systems can be used, whether it is to provide vaccination records, whether it is to provide registries and registration information, whether it is to manage cheat funds, whether it is to manage subsidies or contracts, right? Intellectual property management, rights management, all of those things can be implemented by using blockchain as a transaction management system, right? You can also implement it using, you can also implement some parts of it using existing database with write-only operations, right? But as we will see, blockchain brings in a few more things with respect to tokenization, with respect to decentralization that is not available in the current generation of systems, right? If there are no further questions, we are,
Okay, I have one question, sir.
yes, yes,
This is a distributed system, right? So, how the user or the node can be connected to the blockchains, and how the where actually the software is stored, and how it is accessed, like that. Suppose you
so
are whenever you are opening a application in a mobile, how this mobile server, where the mobile server actually situated, and how it is maintained, means this is a distributed system, no single company maintain it, right?
right, right. So to
So
answer
just
that
to
question,
give some knowledge about that who developed this applications, how it is stored in a system, and how many companies are doing collaboratively to do that, like that. Okay.
So there are so many companies, right, which are contributing to the web, what is called the Web 3.0 landscape, right? Now, typically, there are two parts to a blockchain system. One part is the infrastructure part, right? And the second part is the application part of it, right? Now, what happens is if you are, for example, using Ethereum, on top of Ethereum, you can use a Ethereum token to create a new blockchain mechanism, right? So in that case, you are running on the Ethereum infrastructure, or in many cases, the infrastructure can be run privately. India has been talking about creating its own blockchain infrastructure. So this is something that we are in that case, MELT is one of the organizations, or SIDA is one of the organizations tasked with building infrastructure itself. Now, on top of this infrastructure, somebody may use the tokens that this infrastructure is generating for building their smart contract system. Right? So, from a distribution perspective, it will boil down to that particular application, right? In terms of how you want to architect it and where do you want to store the value. The end point of a mobile of a cryptocurrency can be an exchange which is maintained by a third party, and the exchange in turns it stores the private keys of all the users, and it can provide app for its end users, right? That kind of architecture is possible, and most of the cryptocurrency exchanges that we are seeing now are following that particular model, right? Whereas it is also possible that we let go of the exchange and the security keys are being by right? In which case the distributed code is being run all across, right? There is no single computer, right? So if I look at uh, one of the challenges that we're seeing with blockchain systems, wherever we have had this kind of centralized implementation of one person or a group of or a company kind of running the exchange, any failure on the exchange meant that or any infiltration on the exchange meant that the entire users' wallets were all gone, right? So to answer your question, it could be a third party which is hosting it, or it could be completely. It would go in a completely distributed model as well. In which case, whoever is becoming part of the network, whoever is agreeing to become part of the network by exchanging keys with the existing deployment, becomes part of the network itself. I hope that answers your question.
Actually, in that case, you have to develop the architecture or storage network or something GPUs like that.
It is there. So that, yeah, exactly as you pointed out, right? That is where infrastructure. I mean, blockchains are themselves built in different architectures. There are private blockchains, and then there are public blockchains, right? In case of a private blockchain, it is the entity. For example, it could be a private bank which is developing its own infrastructure. So in that case, they are the owners, and the operators are kind of given different permissions on top of that. So you can have private blockchains, and you can have something like a Bitcoin, which is a public blockchain. So every time you want to connect with the Bitcoin network, you just say that yes, I want to connect. So you exchange your keys with the Bitcoin network, and then you download your copy of the transactions, or the number of blocks, whatever previous 100 blocks or 200 blocks or whatever number of blocks you wanted to download, right? You join an existing network. It started off with Satoshi Nakamoto kind of setting up something, and then from there it has kind of propagated on, and that's why it's distributed. Right, and down the line, the government may form a separate PSU to kind of launch its, to maintain the infrastructure for the blockchain infrastructure for India.
So in that case, we have heard that the no intermediates are there, right? So in that case, the owner of the company will have some. If the owner of the company for that, then in that case, all the wallet amount will be gone for that also.
Yes, yes. So that is why I'm saying that there are multiple architectures that are possible, and it really boils down to what are your requirements in a particular application, right? If you are creating a wallet, like if you're creating cryptocurrency, then permissioned or private blockchains may not be suitable at all, right? In that case, you are looking for public blockchains, whereas if your application requires essentially a replacement of an existing database a system, right? In those cases, a permission blockchain, a private permission blockchain can be, can give you tremendous speed trading of the decentralization. Right, I will get into this tomorrow.
Okay, sir. Okay, sir.
Because I did not get into different kinds of architectures, because when a bank runs this, they want the benefits, they want the tokenization
Right,
benefits, they
sir.
want benefits of certain benefits of blockchain, but they do not want the anonymization because it is running within their network. They are trusting their own network. So it depends on how much trustless you want to be. You have multiple options that are available, and to a large extent, the government actually proposes a framework. Just getting a little ahead of myself, but we will see how there is a framework in place which decides whether you need to use a public blockchain or a private blockchain, depending on the number of stakeholders you have, the kind of transactions you are dealing with, the entities of who's creating the transactions, what kind of write permissions or read permissions you need in that network. And we'll get into this tomorrow. But thank you for your question. Right, Reshmi, we'll call it. We will end the session here. Thank you, everybody. Thank you, everybody, for listening in. Thank you all for your time.